Okay, hello and welcome back. Today we're going to start section 6.1. We're actually going to kind of break that section up a little bit. So we'll do part 1 today on power series. So if you need a little Calc 2 refresher, you're in luck. We have lots of fun Calc 2 style problems in this one. So this first one, we're going to find the radius and interval of convergence. So our given series, we're going to go from k equals 0 to infinity of 3 to the minus k times 4x minus 5 quantity to the k. So to find our interval of convergence, the most common way is to use the ratio test. Quick little mini review on that. To do the ratio test, you take the limit as n goes to infinity or k goes to infinity, whatever index you choose, of a sub n plus 1 to a sub n. And if that's some limit L, we take the absolute value so we don't have to worry about L kicking over to a negative. If L is less than 1, we converge. L greater than 1, we diverge. And where L equals 1, the ratio test fails, we have to do another test. So basically, we'll end up doing a pair of sort of test points to see if we get to keep the endpoints or if we don't get to keep our endpoints. All right, so back to our original problem in front of us. So we will do the limit as, in this case, k goes to infinity of all of our k's are now k plus 1s. So 3 to the minus quantity k plus 1, 4x minus 5 quantity to the k plus 1. And we're going to divide that by the a sub kth term, or a sub nth if we had switched over to n's for these guys. So 3 to the minus k, 4x minus 5 to the k. We've got some simplifying work to do there. So limit as k goes to infinity. Let's see, we have distributing 3 to the minus k, 3 to the minus 1. So multiplying with the same bases, you add your exponent, and both of those would be minuses because of distributing the negative. Similar idea here, 4x minus 5 to the k, and 4x minus 5 to the first. So downstairs, we still have our 3 to the minus k. We've still got our 4x minus 5 quantity to the k. All right. So everybody's favorite time to do a little cancellation. 3 to the minus k, 3 to the minus k. Goodbye to those. 4x minus 5 quantity to the k over itself is a nice pretty 1. So 3 to the negative first is 1/3. The 4x minus 5 to the first no longer has k involved. We can just grab that. 4x minus 5 times the limit as k goes to infinity of 1/3. So this is just 1/3 by 4x minus 5. And we would like that to be less than 1. Now, to find out where we are centered, we want the inside to be of the form x minus c, so I'm going to go ahead and factor a 4 from that as well. So 4/3, absolute value of 4 is still 4, 4/3. Absolute of the difference of x and 5/4 is less than 1. So our center is on x equals 5/4. In our radius of convergence, we just get rid of the constant x minus 5/4 is strictly less than. We multiplied both sides by a positive, so the inequality is facing the same way. Less than 3/4. So our radius is 3/4. So I'll start at the center and go left 3/4 of a unit and right 3/4 of a unit. That'll give me the endpoints, but then I do have to test those endpoints to see if they work. Here's our little, that was just our little bit about, a little bit about how the ratio test works. So moving ourselves left 3/4 of a unit from 5/4 would take us to 2/4 or 1/2. So we'll test x equals 1/2, plug that in and see if that diverges or converges. So sum from k is 0 to infinity, 3 to the minus k. 4 times 1/2 is 2. 2 minus 5 is -3. So we want to know if this converges or diverges. So we have sum from k equals 0 to infinity of 3 to the minus k, 3 to the k, -1 to the k. So 3 to the negative k, 3 to the k, those cancel each other out. So this is just the sum from k equals 0 to infinity of -1 to the k. So this is an alternating series. So alternating series, we want two things to happen for them to converge. If we take absolute of a sub n and take the limit as that goes to 0, we want that to equal 0. If we clear that hurdle, then we also want to show that a sub n plus 1 is less than a sub n. In other words, it's decreasing for all the n in our series. And in this case, we don't make it past the first hurdle, though. Limit as k goes to infinity of absolute value of -1 is just 1. I'm adding just a bunch of 1s forever. That will diverge. So this tells me I don't get to keep the endpoint positive 1/2. I am running out of real estate, so we're going to move our 5/4. Now we're going to move it to the right 3/4. So that's 8/4, which is 2. So we're going to test out x equals 2 on our next page here. So now we have the sum from k is 0 to infinity. We still have our 3 to the minus k. 4 by 2 is 8. 8 minus 5 is 3. So 3 to the k. And we run into kind of the same problem as before. It's not an alternating series this time. It's just plain old 1 to the k. So just 1 plus 1 plus 1 plus 1 plus 1 forever. So this diverges as well. So we don't get to keep either of our two endpoints. So our radius of convergence which we denote with a cap r. Recall from the previous page that that was worth 3/4. And our interval of convergence We did not include either endpoint, so from 1/2 to 2 exclusive on both of those. So a nice opportunity to review a little bit of your work from your Calc 2 days. Hopefully fairly fresh in your mind. Sorry, I am working out of a hospital parking garage today. Sort of an unusual place for an office today, but that's where I am today, so that's where I'm working from. Okay, so our next one at bat here, we're going to use a table. So they're asking about McLaren series. I'm not going to ask that you have a table of McLaren series memorized. I'm going to give you the table, put it to work. If you're looking in the same edition textbook as I am, this is on page, the table is on, I believe it's 234. Power series for, what was it, x e to the 3 times x. So the most similar one that we have in a table of McLaren series is that e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Summation notation, that would be a sum from n equals 0 to infinity of 1 over n factorial x to the n. So this time we want x e to the 3x, which means that I'll have another x outside, and all of these x's inside are going to be now 3x's. So 1 plus 3x over 1 factorial plus 3x quantity squared over 2 factorial plus 3x quantity cubed over 3 factorial plus ... So we'll do a little simplifying before we write it up in summation notation. So this will then turn into x plus 3 to the first, x to the second over 1 factorial plus 3 squared, x to the third, so x squared, and we also have this x being distributed, over 2 factorial plus 3 cubed, x to the fourth, over 3 factorial plus ... on forever. So now we're ready to just describe to the reader what that looks like. I'll keep the initial index at 0 since that's the way the author did it for this one. I'll just keep with the chosen starting point. So from 0 to infinity. So this is our 0th term, and we got x to the first, so that sounds like an n plus 1 to me. We have a 0 factorial downstairs. 0 factorial, remember, is defined to be 1. That was just by definition. So notice that the factorial matches the index. So we have our n factorial downstairs. And notice also that the exponent on the 3, we could attach a 3 to the 0 here if we wanted it there and not change the value. So 3 to the n. So this is our power series representing this. And again, this part you do not have to have memorized. This part, you're just picking it out from a table. Let's make sure my light stays on. Yeah. Okay, so next up, we're going to find the first four terms given, again, the table of Maclaurin series. So we're looking at tangent of x, and they want the first four terms. Now our table is not going to have tangent of x, it'll just have sine and cosine. So we'll turn this into sine x over cosine x. So we're going to need to do a little bit of division here. So sine x be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Downstairs we have 1 minus x squared over 2 factorial, 2 factorial is still just 2, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. So a long division problem is in our future. It's going to be set up kind of in a different way than we're used to. It's going to be set up in ascending order, and we can do that basically because we end up going forever on both of these. So the usual inside-outside for long division still holds, though. Denominator outside, numerator inside. 2 factorial is just 2. 4 factorial, 24. And 6 factorial, 720. And since we only need the first 4 terms, I'm just going to do 4 terms of each of these guys as well. So inside we have x minus x cubed over 3 factorial is 6. X to the 5th over 5 factorial, $1.20. X to the 7th over 7 factorial would be 5,040. 6 factorial is 720, and 720 by 7. So we're going to look at the start of each, and 1 I would multiply by x to hit my x. So then I'll go here. So 1 times x is x. 1 times minus x squared is minus x cubed, and hang on to your over 2. X to the 4th times x plus x to the 5th, hang on to your 24 denominator, and so on. And again, we're only interested in the first 4 terms of this anyway. After you're done multiplying in a long division problem, you flip it. Flip all those signs. Okay, so we have negative 1/6 plus a half is positive 1/3. So a third of x cubed minus 1/30th of x to the 5th, and plus 1 over 840 x to the 7th plus da 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 da. So these just, especially fractions like that, just use the calculator and put it back into fraction. Most calculators have a command where you can turn it back into a fraction. All right, so now I'm looking at what I can multiply 1 by to hit 1/3 x cubed. Sounds like 1/3 x cubed would be a good contender. For some reason I want to write 13 though. 1/3 x cubed. So 1 times anything is that anything. So we have our 1/3 x cubed. And then we have a positive by a negative. Then I'll kick it over to a minus. X squared by x cubed is our x to the 5th. So that's still lining up nice. And a third by a half is a 1/6. X cubed by x to the 4th is x to the 7th. And 1/3 by 1/24th would be 1/72. And again, I don't care what's happening after that, so I don't have to put my x to the 9th down here. They only asked me for the first 4 terms this time. Once again, we're just flipping some signs here. So a minus, a plus, a minus. These two drop, that's what we wanted. So negative 1/30th x to the 5th plus 1/6 x to the 5th. So negative 1/30th plus 5/30ths is 4/30ths, which is 2/15. So 2/15 of x to the 5th. And then minus 4 over 3/15 x to the 7th. Again, I want to match this. 1 times positive 2/15 x to the 5th will get us a 2/15 x to the 5th. So this time I only need 2 of them. X to the 5th by x squared will get me the x to the 7th I'm hoping to line up with. Positive by a negative is a negative. And our 2's drop, so we have 1/15 there. And again, flip your signs. So we have negative 4 3/15 plus 1/15 gives us 17 3/15 x to the 7th. And 1 times that same thing, that's 17 3/15 x to the 7th, will get us back to 17 3/15 x to the 7th. So there are our first 4 terms. And this would go on forever. So there's the first 4 terms. Would be x plus a third x cubed plus 2/15 x to the 5th plus 17 3/15 x to the 7th. So sometimes we do have to do a little manipulation with the stuff on the table. But again, I'm not going to ask you to memorize what's on that table. All right, so then just a couple more shorter examples involving manipulating the summation notation. All right, so they're going to give us this one we started with from n equals 8 to infinity. That is a messy infinity there. What did I pick? 2n plus 5 c sub n x to the n minus 6 power. So I want it to be just x to the k power. So what I start with is just, okay, well, where did they start based on the index? So if I plug an 8 in here, 8 minus 6 is 2, it'll start with an x squared. So that means my k is going to start at a 2 since they want it to be of the form x to the k. Pushing to infinity is always just pushing to infinity. So my n minus 6 got replaced with a k, so n is k plus 6. So then I have 2 by k plus 6 plus 5. C sub n turns into C sub k plus 6. And x to the n minus 6 becomes x to the k as requested. So summation notation involving x to the k. We just had to adjust our index there and just a little bit of cleanup to finish it off. So k equals 2 to infinity. So we would have 2k plus 17 times c sub k plus 6. X to the k. So we changed how it looked, but again, we had the desired result. They wanted something involving x to the k. Now, occasionally they have us perform operations on the power series, and they want us to write it as a single power series. And again, they're going to request an x to the k here. So let's see what they start us with. From 1 to infinity of n c sub n x to the n minus 1 power plus 3 times the sum from n equals 0. So notice the indices do not match yet. Approaching infinity, c sub n, x to the n plus 2 power. Okay, so first I want to get both of these looking like x to the k. So on this one, if I plug in n equals 1, 1 minus 1 is 0, I want to start at x to the 0 power. So that means my k is going to start with an index of 0. So that means n minus 1 gets replaced with a k, so n is worth k plus 1 in this first one. So we're still approaching infinity with our sums. So this n is now a k plus 1. And we just throw the parentheses around it. C sub n is now c sub k plus 1. And x to the n minus 1 is now x to the k. Plus 3 times the sum. And we'll see where we start. So this one started at 0. 0 plus 2 is 2. This one, they want us to start at x squared. So to start at x squared and have the form x to the k, k is going to start at 2. So n plus 2 is the same as k, n is k minus 2. So we have c sub k minus 2, x to the k. So we're getting closer to where we can add these guys up. However, the indices don't match yet. We do have them both looking like an x to the k power, though. So what we can do is just take care of these first two. Take care of k equals 1 and k equals 0 and k equals 1. I apologize, I'm pointing to the wrong one. To match up the k equals 2, we take care of the k equals 0, k equals 1, and then we'll have our sum from 2 to infinity. So letting k equal 0, then we have 0 plus 1, c sub 0 plus 1, x to the 0. So at k equals 0, this thing is just 1, c sub 0, x to the 0, or just c naught. Let k equal 1, and we have 1 plus 1, c sub 1 plus 1, x to the 1. So that's 2, c sub 2. 0 plus 1 should be a 1. I don't know where that 0 came from. So that should be c sub 1 as well. 2 c sub 2 x. So with those two in hand, I'm going to rewrite this starting at 2, and I'll just have c1 plus 2c2x. So now my index starts at 2, which does match up with the other guy. We're still approaching infinity, and we still have the form of so we still have the same form from the other page of k plus 1 times c sub k plus 1. And then in our next one, we had, we're going to pull the x to the k to the end of the line. Then we had plus 3 times c sub k minus 2 times x to the k. So then this is the closest we can get to having it under one roof with summation notation. We just had to deal with 2 extra terms that were not part of the sigma notation just because they didn't fit the pattern. But now they're both referring to the same x to a single power, and it's the summation part is all under one roof. We just have these couple extra terms along for the ride. So far, what we've tried out in 6.1, and I've lost my red pen, shoot. Oh, there it is. Can't have gone too far. So in 6.1 so far, I would try out 1 through 29 in the odds. If you have trouble, get in touch with me. Otherwise, I will see you next time. Stay safe out there.